Welcome, ninth grade extended students. Today we're going to talk about a few more definitions and then I'm going to give you guys some time to work. So let's get started. So the first definition that I need to discuss is that of a half plane that's determined by a line. So let's read the definition and talk about what everything is. Now, before I really start, I just want you to know that a half plane is if I have a plane and I draw a line in it, a half plane is just one side of that line. So all the points that are on one side would consist of a half plane. An open half plane has a line that is not included. You'll notice that this is now drawn in red. So that's what a half plane is. Let's check out the formal mathematical definition. So let's let pi be a plane and let A and B be distinct points in pi. So I have my plane here, distinct points A and B. And we're going to let L be the line AB. So I have these points and I form a line that contains both A and B. Then L determines two open half planes, one consisting of all the points x in pi such that XAB has positive circular orientation. Now let's check this out. See, x is in here. XAB, counterclockwise, is a positive circular orientation. So we're talking about all the points on this side that create that positive circular orientation. Whereas the other consisting of all points x in the plane such that XAB has a negative circular orientation. So now we're going to be actually talking about this side here. If I made that x, XAB would be clockwise or negative, has a negative circular orientation. So I have this line in the plane. One side is one open half plane, the other side is the other open half plane, and the open half planes do not include any of the points on this line. Now let's continue with the definition. For all subsets F of pi, F is a closed half plane determined by L, if and only if, for some open half plane H determined by L, F is equal to L union H. So what is this saying? It's saying, well, right now I'm looking at this open half plane. It does not include the line L, which is the line AB. But if I did include the line, so it was the line and this open half plane, then we would call it a closed half plane. And that's because all the boundary points that would be on this line would then be included in the figure, so it would be closed. Next, let's talk about the open half plane determined by the line L and containing the point x. So this is just some notation here. So when we want to name that half plane, we name that line that creates it and a point that is in it. So let pi be a plane, let L be a line in pi, and let x be an element of pi that's not on the line. The line L determines two open half planes, as I said earlier, H1 and H2, say such that H1, L, H2 is a partition of pi. Then HLX is the unique member of H1 and H2 that contains x. Now let's make some sense of this. Okay, so if I were to draw a line in my plane, I would have all the points in the plane would either belong to this open half plane or this open half plane, or it would be a point along this line. So that's what we say is a partition. If I take all the points in the plane and every single point belongs to something, some points belong to H1, some points belong to L, some points belong to H2, belongs to exactly one of those sets, then it's the partition of the plane. In other words, I'm taking that plane and I'm dividing it into groups. Okay, so if I want to name a specific half plane, let's say I want to name this one over and above that line, I would name it H sub L. It's the half plane created by the line L and containing the line at the point X. So that's how we name a half plane. I'd like you to look now at exercise 227, and it is a proof, and we're trying to see that the circular orientation of AXB is not equal to the circular orientation of CXB. So, and that's in a linear pair of angles. So we're just going to complete this proof. And the way it goes is you are going to look at circular orientation and say that they're the same or different, and then we're going to take a look at it. So give it your best shot. I've provided you with property A1 for your reference if you'd like to see it. And then press pause on your video, and when you're ready for the answer, press play again. Okay, here is my answer. So we're going to start with the circular orientation of AXB. AXB, you can see, has a negative circular orientation, and that's not equal to BXA when I reverse it. Then further, this is not equal to BAX. BAX is not the same as BXA. BXA is counterclockwise or has a positive circular orientation, while BAX is clockwise, which would have a negative circular orientation. Going further, the circular orientation of BAC is here. You can still see that it's clockwise, so that also has a negative circular orientation. I'm going to start adding some words here. This is negative, this is negative, this is positive. So now let's continue on. The circular orientation of BCA. BCA, notice it's counterclockwise, so it has a positive circular orientation, and that's not the same as the one right prior to this. And this is equal to the circular orientation of BCX. BCX, counterclockwise, positive circular orientation. Further, that's equal to the circular orientation of CXB. CXB also has a counterclockwise orientation, so it is also positive. Now you can see here that we have an odd number of equal signs, which would then mean that the circular orientation of AXB is not the same as the circular orientation of CXB, which should have seemed pretty obvious from the beginning of this problem because we can simply just look at it. But that is how you would prove it. Next, I want to talk about how we can tell if points are in the same open half plane besides looking at it. So if we let pi be a plane and we let L be a line in pi, then for all points x and y in pi that are not on my line, such that x and y are not the same, I know that they are in the same open half plane if and only if my segment xy does not intersect L. So notice over here, x and y are in the same open half plane. They are both to the left because my segment does not intersect my line. Whereas over here, x and y are in different open half planes because my segment does intersect the line. And that is the definition of points that are in the same open half plane. Finally, I want you to note that every open plane is a convex set. Remember that a set is convex if I can find any 2 points in that set, such that that segment that connects them is always in the set. And you can see here, if I take a point P and Q in the same open half plane, I draw that segment. Nothing I can do would create a situation where that segment is not entirely contained within that open half plane. So it is absolutely a convex set. The other thing to note is that planes are essentially bisected by every line reflection. So if you have a line and a plane, this side would reflect onto the other side and vice versa. It cuts that plane into 2 parts. I also want you to understand what it means for a function to have restricted domain. So if you imagine you have a function with a domain of A and a range of B, it's like this. F goes from A to B. But if there's a subset of A, I can define a different function so that it's defined the same way, except that I'm restricting the domain to only a subset of A. So G would be from C to B, same range, for all x and C, and G of x would equal f of x. Now let's put this in terms of something you've seen before. So you might recall from the last review sheet, I defined a mapping of all the points in space onto this sphere. So if my point was on the center, then that point would get mapped back to itself. Otherwise, if the point was not on the center, it was this point P, where the point P is the intersection of my ray formed when I draw it from T through X, and it was the intersection of that ray with my sphere. So in this case, X would get mapped back to that surface. So all the points in space are getting mapped back to the surface of the sphere, except the center point, which gets mapped back to itself. Now, in this case, my domain is the set of all points in space. However, I could restrict the domain to include only certain points. In this case, I'm going to define a set of points that are inside the sphere and including the surface of it. And I'm going to call that C. So C is equal to the set of all points x such that the distance between T and X is less than or equal to the radius of my sphere. So it's all these interior points. Well, I can restrict the domain so that I'm only mapping these interior points, and I would call that F hook C. F with restricted domain C. C is a subset of all the points in the plane. And this is actually a different function, but all the points that are inside the sphere get mapped to the same location as they would have in F. It's just I'm not doing anything with the points that are outside the sphere. So that reads F hook C, and again, that's restricted domain. And here's one more property of translation. Let's read the mathematical property, and then I'm going to draw a picture so that it makes a little bit more sense to you. So this is T6. We're going to let pi be a plane, and we're going to let T be a translation of pi such that T is not the identity mapping. So in other words, I'm reflecting over a set of parallel lines, but those lines are distinct. They're separate. Then T is equal to the composition of these reflections for some lines K and L in pi, such that K is parallel to L. And for all lines M in pi, M is a fixed figure of T if and only if K is perpendicular to M. So let's draw a picture of this. So I have these lines, L and K, and they are parallel. And it is creating a translation. So I would first reflect over K and then reflect over L. And I'm wondering, where is this fixed figure? So what this says is that a line is a fixed figure if and only if it is perpendicular to this line K. So now let me just draw a picture of this so that this makes some sense to you. So here is my line M. So if I have this line that's perpendicular to K, it's perpendicular to one of two parallel lines, so it is now perpendicular to the other. If I take any point on this line and reflect it, it will still be on my line M because it's perpendicular to K. And then if I reflect it over L, it'll still be perpendicular. It'll still be on M because L is perpendicular to M. So all these points are going to slide over, but they still will be on line M, and therefore there will be no fixed points, but M will be a fixed figure because when I'm done shifting it, all the points are still on M. So right now I have some work for you on Schoology. I would like you to do that for homework tonight. Have a great night. See you tomorrow.